So, Dr. Ken Walsh, he's an associate professor of civil engineering, and his talk today, as you can read, is Preparing for the Big One, Protecting Critical Infrastructure. It's all yours.
All right, thank you very much. Everybody can hear me okay? Oh, thanks. Yeah. Appreciate it. So again, my name is Ken Walsh. I'm an associate professor in the Department of Civil Engineering here at OU. My civil engineering has a lot of sub-disciplines, and so the sub-discipline that I focus in is structural engineering. And so structural engineering is involved with designing things like buildings and bridges. My research area, though, is in seismic protective systems. So I look at designing and developing systems to reduce the effects of earthquakes on structures. And so today, I'm going to talk to you a little bit about earthquakes, what the effect of earthquakes on structures are, what those effects are, and ways in which, traditional ways in which those effects have been mitigated, and then some of the research that we're doing to improve seismic protection systems. And so the first thing I want to talk about is I'd like to talk a little bit about earthquakes and what the effect of earthquakes on structures is. So when an earthquake occurs, we have a large release of energy, right? So we can think of this problem in terms of energy. So a large release of energy, and that energy is absorbed by everything that's on the ground in the vicinity of the earthquake. And that includes all our structures, buildings, and bridges. And so that ground shaking from the earthquake translates to shaking of the buildings and bridges. And the shaking of the buildings and bridges can be characterized by the deformation of the members that make up the structures, and also how fast the structures are accelerating. And so those are the two things that we're concerned with most. And the reason we're concerned with those things is because the deformation of the structural members results in damage to those members, which could lead to, in worst case scenario, collapse of the structure. And then the accelerations are important because the acceleration affects the contents of the structure. So everything in the structure is affected by the acceleration, right? And so we want to reduce the effect, we want to reduce the damage in the structure itself, and we want to reduce the damage to the contents of the structure. And so I thought it's been a long time since we've had a major earthquake in the United States. The last major earthquake we had was in 1994 at the Northridge, California earthquake. And that was a devastating event, but that's almost been 25 years now. And so it seems like a lifetime ago. And so I thought the first thing that I would do is show you some pictures of some damage that happened during that earthquake. So this is in California, 1994. And so this is a parking structure on California State University that collapsed. And you can see here the whole parking structure collapsed into itself. This is a picture of an apartment building that collapsed. And the way these apartment buildings used to be designed is they would have a carport underneath the apartment. And so that carport created what we call a soft story. So you have a lot of weight above it, but not a lot of strength in the carport itself. And so when the horizontal shaking of the ground comes, it shakes all that weight above the carport, and then the columns holding up that apartment failed, and it literally just collapsed on the cars underneath. So these are cars that were parked underneath the apartment that got crushed when it just basically pancaked. This is a picture of Anaheim Stadium. So this is in the outfield, and you can see a whole section of the stadium collapsed into the outfield. This is a picture of collapsed highway, Route 19, where two sections of both directions collapsed. And this is another section of a collapsed highway at Interstate 5. And so you can see the effect of this earthquake was just devastating. And I think the earthquake, there were around 60 fatalities. Something like 3,000 people were injured. And in terms of cost of property, it's the second costliest natural disaster in our recorded history after Katrina. So it was a major event, and it caused a lot of damage, and we learned a lot from it. All right, so This is so that was a 1994 earthquake, but I don't want to make it seem like that was an isolated event. So in 1989, there was another earthquake in Loma Prieta, California, and this is a collapsed house that occurred during that earthquake. And then back in 1971 in San Fernando, California, this is the Olive View Hospital, which basically also collapsed. So we've had several large earthquake events. All of them occurred a long time ago, but obviously we can have another large earthquake at any time. In fact, they say that we're due for our next large earthquake. And again, we've had lots of earthquakes throughout the 1900s. We've had earthquakes in Alaska, major earthquakes, Alaska, Hawaii, more in California. And so just with the fact that we haven't had one in a long time doesn't mean this isn't a problem. Luckily, people are working on the problem, right? So people are working on how can we better protect structures from the devastating effects of earthquakes. All right, so we've talked about the devastating effect of earthquakes, and I've talked about this idea that your building, you get these accelerations and these deformations of your structures. I'm focusing on a building here. One way that we can protect our structures from earthquakes is to strengthen them. So actually add more structural members to the structure, so basically make it stronger. And so I have a little demonstration I want to do here to show the effect of strengthening, all right? And so what I have here is a 2-story scale building model, and I've made this out of basically what's like the equivalent of like an erector set. And what I'm going to do here is I've got these weights here. I need to add some mass to replicate the floor weight. So I'm going to add these weights here. And I'm going to ask for a volunteer from the audience. And what I need someone with a steady hand, because what I've got here on the table, this cart, is basically my earthquake simulator. But it's going to require some person power to run it. Does anybody want to volunteer to come up and be my... Yes, you right there. Thank you, sir. You were volunteered. All right. Now, this structure, you're going to find out soon, is... All right, come around this side. What's your name?
I'm Nate.
Nate. Nice to meet you, Nate.
Nice to meet you.
All right, Nate, what we're going to do here, once I tighten this thing down, because I just realized some of these columns are not connected as tightly as they should be, we're just going to give this, I'm going to hold this handle here, and we're just going to shake this back and forth and see what happens to our 2-story structure. Whoa. Nate, you got a lot of energy, Nate. You've been drinking too much coffee. Well, that's okay. That's okay. Let's tone that down just a little bit. That was like a magnitude 9 earthquake there.
Going down to like 7.
Yeah, let's bring it down. All we really want to do is see what happens to our structure here. I got to get this thing back in here so it doesn't slide off again. When we shake it from the ground there. Sorry, Nate. Hang on one sec. I'm not sure that's in. That's in. All right, that should be okay. All right, I'm thinking like this.
Oh.
Yeah, that's okay. That's okay. All right, so there you go. Yeah, that's very good. So, and you can see now what happens is the columns of our 2-story structure, particularly these first floor columns, are deforming. Right, and if Nate went back to his magnitude 9, he might actually be able to snap those columns. And so what we have here is we have sort of a slow kind of rocking motion of our structure, right? So, and if you go a little bit, not so much displacement, but higher frequency. There you go, yeah, a little higher maybe. There you go, yeah. And so you can see we've got large deformations of this structure, and we get this sort of this swaying motion, right? All right, thank you, Nate. Thank you very much. Actually, you can stick around if you want now that you've got the experience.
All right, of course.
Thank you. So now what we're going to do is we're going to add some what's called lateral bracing. So we're going to add some more structural members to it to see if we can reduce that deformation. So maybe you can help out, Nate. I'm going to put these in here like this. See these little diagonal members? Right. They go right in like that.
Okay.
And then we can just I've got some screws over here we can screw them down with. There's two. They just go right in there and right in there. Now, the type of lateral bracing system I'm using here is called a chevron brace. And it's very effective at providing resistance to lateral movement. Again, lateral movement is the predominant type of motion that we're concerned with. Although you do get vertical movement from an earthquake, the effects on the structures are not quite as significant as the effect that you get from lateral movement. So we're going to strengthen this thing, all right? We're strengthening it. And then we're going to rock it again. It may not be lined up there. Let me see. I think it's got to sort of snap in. There you go. I got it. All right, so we put our chevron bracing in, and I put one here on the front and one here on the back. And now we're going to let Nate have at it again. Please, let's not do a magnitude 9, though, Nate. Yeah. Give a little more, maybe. Yeah, maybe higher frequency. There you go, yeah. And so you can see, it's obvious the effect, right? So we have significantly reduced the amount of deformation. But now, it's okay. But let me ask you a question. Now, before we put those braces on, we had sort of this nice rocking motion to our structure. Now that incorporated large deformations, right? Now we've lost those large deformations, but has anybody else noticed a difference in the way it's vibrating now to the way it was vibrating before? Anybody?
Oh, she does.
The top? Up here? And what about it? Shaking more. It's shaking more. It's accelerating more. So what's happened is we've reduced, thank you very much, Nate. I appreciate it. We've reduced the amount of deformation of the structure, but all we've done is increase the amount of acceleration. And so we haven't actually reduced the amount of energy that the structure absorbs from the earthquake. We've just changed how it absorbs that energy. So instead of having these large deformations in this soft sway, we now have these kind of tight deformations, but they're happening a lot faster. And again, remember, we have two things that we're concerned about. We're concerned about the deformations, and we're concerned about the accelerations. And ideally, we would like to minimize both of those, right? So we want to protect the structure from damage, and we want to protect the contents of the structure from being damaged. And so in order to do that, we have to come up with a way to actually get the energy out of the structure. And so the way that we do that is we actually add energy dissipation mechanisms into the structure. So we actually add mechanisms to the structure that are able to take its vibration, its energy of vibration, and dissipate it, or absorb it into themselves and dissipate it from the structure. So one of the most popular type of energy dissipation devices is called the fluid viscous damper. And a fluid viscous damper is much like a shock absorber that you have in your car, except it doesn't have the stiffness component. A shock absorber in your car has a damping component and an elastic component, like a stiffness component, to provide a nice smooth ride. The fluid viscous damper only has the damping component. And the way that this damper works is you've got this cylinder, so this big body here, you've got this cylinder, and the cylinder is divided into two chambers. So we've got a volume over here, one chamber over here, and we've got this other chamber over here. And what's dividing it into those two chambers is this piston head here, which is connected to a piston rod, which extends out, in this case, both ends of the cylinder. Now, inside the chambers, we would have some sort of viscous fluid, like an oil, all right? And what happens is, you can barely see here, it's denoted the orifice, but there's a little bit of space between the piston head and the wall of the cylinder. So there's a little bit of space there. And what happens is, as you drive the piston, it takes the fluid on this side and squeezes it through those orifices onto this side. And as that fluid is squeezed through those orifices, it's sheared. And it's basically like friction between the layers of the fluid. And that friction causes the fluid to heat up. And so what we're able to do is we take the mechanical energy of this piston moving back and forth, and we can convert that mechanical energy to heat. and then that heat is dissipated through the body of the damper. And so if you take your structure and you put enough of these fluid viscous dampers in your structure, you can actually dissipate quite a bit of energy. Now, I actually have a demo of a fluid viscous damper sitting right here in front of me. And so Nate, no, I'm just kidding. I would like to do another demonstration on the fluid viscous damper. Is there anybody else who might be willing to volunteer to come up here and do a demo on the fluid viscous damper? Yes, you next to Nate. Thank you so much for volunteering. You guys are mean to each other. All right, so what I've got here is not actually a fluid viscous damper, all right? What I've got here is called a pneumatic damper. There's no viscous fluid inside this, it's just air. But it actually functions the same way. And so what I'm going to do is I've got, so this is constructed similar to the way this is constructed, except there are no orifices here, right? So we've got this cylinder, we've got two chambers, but the fluid can't move back and forth between the chambers inside the cylinder. But what I do have on this one is I have these ports, these holes at either end of it, and so the fluid can move in and out of those holes, all right? And so what we're going to do, and you can hear it's air, so you'll be able to hear it. You hear that? It's pushing the air in and out of those chambers, all right? And so I'm going to ask our volunteer, what was your name?
Liddy.
Lydia?
Yeah.
Or just Liddy?
Just Liddy.
Just Liddy.
Yeah.
All right, Liddy. So Liddy, I'm going to ask you to, we'll just try pushing that piston back and forth. You feel any resistance?
No.
Not too much resistance, right? All right. Now, one of the things that affects the amount of energy that's dissipated by a fluid viscous damper, or the force that the damper produces, is the size of the orifice that the fluid moves through, right? So the smaller that orifice gets, the harder it is to push that fluid through. And when that fluid goes through, the larger the shear rate, so the more friction you get. The other thing is the viscosity of the fluid, but I can't control the viscosity of the fluid here because we're using air, all right? But I can control the size of the orifice that fluid is moving out of. So I'm just going to close these up a little bit. I'll try that, Liddy. That get harder?
Yeah.
Got harder, okay. All right, so what we've done there is we've increased the damping coefficient by reducing the size of the orifice. And in theory, if we install this in a building, it would now dissipate more energy. All right, the other thing I wanted to try here, Liddy, was this. I'm going to pull this back. I want you to try two things. First, I want you to take that piston, if you could, and slowly move it in. Fairly easy to do?
Yep.
All right, now let's bring it back out. And this time I want you to try to put it as fast as you can. How'd that feel?
It was good.
Harder?
Yeah.
Harder to do, right? Yeah. So the force that comes from a fluid viscous damper is dependent on the velocity that you actuate the piston. So if you do the piston nice and slow, it doesn't produce that much resistance. But if you try to really squeeze it in there hard, it produces a lot of resistance. It's a lot like the dampers that are on your screen door, right? You go to close your screen door really fast and you can't do it, but then if you let it sort of just ease close, it closes nice and easy, right? Thank you, Liddy. So the reason I'm bringing all of this up, is because it's an important concept in energy dissipation, all right? So if I were to draw a plot, I know nobody likes plots, but this is going to be an easy plot, I think. I'm going to draw a plot and sort of an XY plot here of the force that's coming from that damper. So the resisting force as a function of the velocity of how fast I'm driving that piston back and forth. So I got an arrow here, I got one up here. I'm going to call this force of the damper, FD, and I'm going to call this the velocity of the damper, x dot, which is a derivative. That's probably not a good thing to use. VD, all right? And if I plot that, it looks like this. It's a linear plot, right? So the amount of force that comes from the damper is directly proportionate to how fast you drive that piston. Now, if, and I'm getting to the point, if I want you to know this is my first time ever using a flip chart. If, I'm going to put this up here for now. Well, no one can see it. I don't have anywhere else to put it. So now if I were to plot the force as a function of the position of this piston, so how far it moves or how much it moves, right? Then that plot would look like this. By the way, I'm left-handed, why it looks goofy when I'm writing with my right hand. I didn't set this up right. So if I plot the force as a function of the position, so now I'm going to call this just X for position, and I'm going to call this FD, still for force. So this is not velocity now, it's position. Then the plot looks something like this. Now, what's important about this plot? The area contained inside this plot, so that area there is how much energy is dissipated by this damper for one cycle of motion. Meaning, if you start, push it in, pull it all the way back out, and go back to its original position, that's the amount of energy that would be dissipated by it. And that's an important concept that I'm going to be talking about later, which is why I'm introducing it now. All right? So if you have a force versus displacement curve, the area that's bound by that curve is how much energy is dissipated. And again, the whole point is dissipating energy, right? We want to get the energy out of our structure. All right, so now I want just to show you. So when we use these energy dissipators, they can be incorporated directly into the structure. So you can put them directly into the frame of a building. You can put them in a bridge between the bridge deck and the bridge pier to dissipate energy between the deck and the pier. And so I've just got a few pictures of applications or installations of viscous dampers throughout the world. So this is in the San Bernardino Justice Center in California. And so you can see this is the viscous damper here and here. Down here is just a brace for holding it in place. And you can see there's two here, but a structure would have many, 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 many of these viscous dampers, such as this one. So this is the Buddhist headquarters in Taipei, Taiwan. And you can see that each of these is a viscous damper. So they're installed on all floors of a multi-story structure. Now this is an example of a viscous damper or a fluid viscous damper installed in a bridge structure. And so I don't know if you can see them, but up here, right in here, are the fluid viscous dampers. And so what they're doing is, this is incorporating another system called isolation. But basically the way that this bridge deck is supported on this pier is through a flexible element that allows relative motion between the pier and the deck. And then these viscous dampers are then there to dissipate that energy between the bridge and the deck.
Question?
Yes, please.
What if the earthquake comes
The other direction. Yeah, that's a good question. Well, yeah, thanks. So the question was, what if the earthquake comes in the other direction? And so what happens is these seismic isolators will help dissipate will help isolate the bridge in either direction. But the energy dissipation will only come in the direction that these dampers are oriented. But that's the type of vibration we're most concerned with, is the bridge moving this direction relative to the pier. So, and then you can see them again here, and again, you can't see, this is a pier here, and then this is the bridge, and you can see again it's installed there. So this is a very common type of energy dissipation system. It's used in all different types of structures throughout the world. Yes?
So does this mean that vibrational energy that hits a bridge cross-sectionally is less damaging than when it's struck parallel? Yeah, well, so does this mean that the energy that is imparted into the bridge transversely is more than the energy that's imparted longitudinally? Correct? Yeah. Basically, yeah.
Yeah. And so I think the answer to that question is, if you recall those images that we saw from the Northridge earthquake, what happened there is the superstructure, the deck, actually came off of those piers. Do you remember those pictures? And so that is the direction of vibration that we're the most concerned with. We're not as concerned as what happens in this direction, because the effect of what's happening in the transverse direction is not as significant or severe than it is what happens in the longitudinal direction, because if it comes off the piers, then of course the whole section of the highway could collapse. Okay, so so anyway, the fluid viscous damper is, as I mentioned before, a very common type of energy dissipation system. It's used in all types of structures throughout the world, but it's not a perfect system. It does have its drawbacks. And so researchers all over the world are working on trying to develop improved energy dissipation systems. So improving upon energy dissipation systems. And I should mention also that the fluid viscous damper is not the only type of energy dissipation system that's used. There are lots of different types of energy dissipation systems. They all have their pros and their cons, and so researchers are always looking to try to improve upon them. And so one type of energy dissipation system that has received a lot of attention over the last decade or so is called a resettable stiffness damper. And the resettable stiffness damper, I actually have a resettable stiffness damper right here. Grace, who's helping me out today, just converted our fluid viscous damper into a resettable stiffness damper for the purpose of this demonstration. All right. Now this is the benefit of the resettable stiffness damper, as I'm going to show you in a second, is that the force is not dependent on the velocity as it is in the fluid viscous damper. Now why is that important? Because if you have an earthquake that has a large velocity pulse, meaning a sudden jerk of the ground, right? That large velocity pulse is transmitted throughout the structure. And if you have fluid viscous dampers in that structure, and their force is a function of the velocity, that means all of a sudden you have these really large forces exerted on your structure. And your structure may not be designed to withstand those really large forces. Also, it's harder to predict what the velocity of an earthquake is going to be, right? However, part of the seismic design of buildings and bridges, part of one of the criteria is the deformation of the structure. So we already know what the design deformation of the structure is. So if we have an energy dissipation device that's a function of the deformation, then it's much more predictable what's going to happen, what kind of forces we're going to get for it. So anyway, I wanted to take a second to explain to you what just happened, because as you can see, our fluid viscous device has undergone a transformation, right? And so what we've done here is we've added what we call a bypass loop, right? And so basically what we've done is we've connected this chamber to this chamber with this hose, and in the middle here I have a little valve. Now that valve is what we call always closed, so it's closed now. Now if I push this little plunger here, it opens the valve, right? Which means that right now, if I were to try to push on this, all it would do is it would just compress the air on one side, and it would kind of act like a spring. But if I push this plunger, it would allow that air to move into the other side, and the pressure would basically equalize. And so now I need another volunteer for another demonstration. Does anybody want? Oh, we got one over here. Thank you so much. The one pointing. Oh, I thought you were raising your hand. And that you were raising your hand? Oh, great. Oh, before I do this, let me get, what's your name? Elizabeth. Elizabeth. Thank you, Elizabeth. I'll pull this off. So what I'm going to do here is I'm going to try to demonstrate the concept of the resettable stiffness damper. All right, and again, all we have to do is keep in mind right now that what we've got here is we've got this cylinder, we've got two chambers separated by a piston head. The flow of air inside cannot pass from chamber to chamber inside. The only way it can pass from chamber to chamber is to come through this bypass loop. But it can only do that when I push this button. All right? The first thing I would like to do is I would like to see if Elizabeth could help me demonstrate this as a spring. Because a resettable stiffness damper can be idealized as a resettable spring. All right? And when you compress air, it basically acts like a spring. What the air will do is it'll store the energy that you impart on it by compressing it. And if you let that piston go, that piston's going to come right back out, right? Because it'll convert that stored energy into kinetic energy and push that piston right back out. Are you ready, Elizabeth? All right. What I'm going to have you do is I'm going to have you push on that piston there. Can you push on that piston? Is it providing some resistance?
Yeah.
Yeah, you can let it back out. Actually, just let it go, see what happens. Try pushing it one more time, and I'll let it go. So you see how the piston comes back out. So now there's a lot of friction in this system. So we got a lot of friction in these seals, which is probably not allowing it to come all the way back out to its original position. But the concept is there, right? You compress that fluid. When you release the energy that you're imparting upon it, it just converts that potential energy back into kinetic energy and pushes it back out. And so, well, try pulling that for me. See what happens when you pull it. You might want to pull it like this thing, just in case. Pull harder, pull. All right, let it go. So it's the same thing. So in both directions, push and pull, it behaves basically like a spring. And so, just 1 second, Elizabeth. If I were to plot this, I'm going to try this left-handed this time. If I were to plot the force from that damper versus the position, it would look something like this. Position on the x-axis, force on the y-axis, and as you were pushing that further and further, did it get harder to push? Would you say, yeah? Okay. So then that force is increasing with the position, right? And what about when you pulled it? Did it get harder and harder the further you went, Elizabeth?
Not really.
Come on. A little, okay. Well, this is the way it's supposed to work. All right? So that is the plot of the force versus the position, the way that it's operating now. Now, if you'll recall from our viscous damper, the only time we dissipated energy is if we had some area bound in the force displacement curve, right? Do we have any area bound in this force displacement curve? No, we do not. Have we dissipated any energy from this system? No, we haven't. All we're doing is we're taking the fluid, storing potential energy, converting that back to kinetic energy, back to potential energy, back to kinetic energy, but we're not actually dissipating any energy, right? So as it is, as a spring, it's not helping us. All right, so now let's try something different. All right, Elizabeth, we have to be careful here, all right? So now what I'm going to do is I'm going to hold this plunger, and Elizabeth is going to push on that piston, and when you get to as far as you can push, I'm going to hit this button, all right? Now, when I hit this button, there's a good likelihood that is going to sort of fire forward. So at that point, you want to try to let off of it a little bit. We'll try to time this, all right? Are you ready? All right, here we go. So she's going to push it. I'm going to hold this side. Yep. Are you ready? You feel it? What happened?
It was easier to push.
It was easier to push. It lost all of its resistance, right? All right, now I'm going to get it back out to where it was. All right, now try pulling that. Pull, 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 pull. Ready? Did you feel it? What happened?
It was easier to pull.
It was easier to pull. And so basically what we're doing is when she pushes it, she's storing the energy in the cylinder. When I push this button, it's taking all that stored energy and dissipating it as the air moves through the system into the other chamber. In other words, the force builds up. When I push the button, pressure equalizes, the force drops to zero. And then as she pulls it the other direction, the force builds up. I push the button, force drops to zero. Thank you very much, Elizabeth. Now, if I plot what I just described over here, oops, I got to get this off. Ran out of room. I'm going to cover up my viscous damper plot. So, if I plot what I just described, and again, I need X and Y, force in the damper on the Y, position of the damper on the X. Now, we just said, as Elizabeth described, as she pushed on the piston, that force built up, right? We got a larger and larger force. When I pushed the plunger, what happened, Elizabeth? It's easier to push. All that resistance went away, right? So basically, that force dropped to zero. Now, as she pulled it again, That force built up, built up, built up, built up. And then what happened when I pushed the plunger? Force dropped to 0, right? And if we continued that, I'm going to get on my thing, it would look something like that. And so now, what do we have? Do we now have area bounded by our force displacement curve? Yes, we do, right? Now we have all this area bounded by the force displacement curve. And so now our damper is dissipating energy. Yes?
Who pushes the button?
Thank you. It's like the perfect segue. It's almost like we planned that. Who pushes the button? So the way that this damper works now is it uses a combination of a sensor, a computer, a electric valve, and what we call a feedback loop. And so the sensor is actually on the piston of the damper, and it's measuring the piston position. It's sending that information to a computer. The computer is taking the piston position and determining when there's a change in direction, because it ends up that we can get the most energy dissipated if we push the plunger every time the piston changes direction, because that's basically a maximum displacement of the piston, which means we've stored the most energy, right? And then when the computer detects there's been a change in direction, it sends a signal to the valve, and the valve opens and closes. Electric valve in practice. Valve opens and closes. And that system is called a semi-active control system, because it all works on a battery, right? Because if you have a sensor and you have a computer and you have an electric valve, then you need a battery to operate all those components. And so the problem with that is that having all of those different components compromises the reliability of the system. Because if any one of those components, the sensor, the computer, or the valve breaks down during an earthquake, then you've lost all damping to your structure. Well, for that damper anyway, right? And so I was studying this system maybe 9 years ago, and I was looking at the system and I was thinking to myself, the concept is fairly simple. As that piston is driven back and forth, when it reaches its maximum position and then changes direction, you want to push the plunger. You want to reset the damper, right? But in order to achieve that, it relies all of these components, sensors and computers and electric valves and batteries. I wondered to myself, is there a way we could simplify this? It's a fairly simple concept that uses a fairly complex system. And so I was wondering, is there any way to simplify this using a mechanism, like a mechanical way to actuate that valve? And so what I started thinking about was... Oh, she's so good. What I started thinking about was I needed something that as the piston was driving to its maximum position did absolutely nothing, right? But when that piston changed directions, it needed to be engaged. And so I thought to myself, what simple tool do we have that does absolutely nothing in one direction, but then as soon as you turn it back in the other direction, it's engaged? The ratchet, right? The problem is that I only need to be engaged for a minute, a second actually, when it moves back in the other direction. And then I need to be free again. Now you remember, you guys probably all familiar with the ratchet, you've got this little lever on the ratchet, right? Which basically allows you to change what direction is free and what direction you have resistance, right? So if I had something like a ratchet where I could switch the lever back and forth at a maximum position of the piston, then maybe I could use that system to achieve resetting. And so I came up with this idea. This is called the rack lever. It's because it uses a rack and a lever. All right, now the way this works is I've got this grooved rack, and resting in this grooved rack at some angle, I've got this lever, right? Now I'll start on this side over here. If I move the rack this way, nothing happens, right? But as soon as I push the rack back this way, these grooves engage this lever and it drives this part here up vertically. See that? So now I've got a way to move this back and forth and only have this vertical motion at a change in direction, all right? So, and it doesn't matter how far I go all the way out, or I could just go halfway. obviously in an earthquake, we have no idea how far the displacement of the piston is going to be, right? So the system has to work for any change in direction in any position. And so then I thought to myself, well, if I take my plunger, it's okay, I don't need it. It's okay, yeah. If I take my plunger and I mount it up above this, right? And I attach that system back to my damper, and I attach this to the piston, then basically I can drive the piston in one direction, compress the fluid in the damper. When it changes direction, it'll actuate the plunger on my valve, which will open the valve, allow the pressure to reset, and then close the valve as it comes back down, and then start storing energy as I drive the piston in that direction. And so we actually brought that system here with us. So the thing is, I have this here because the actual rack lever is really small and you can't see it. So that's the concept. Just going to take a second to set this up. And so what we did is, based on the idea, we designed an experiment. And we basically used the same components that you already saw before with our resetting damper, resetting stiffness damper. But what we did is we attached the piston up to this rack. And the rack is free to move back and forth. And then above the rack we have our lever. And then above the lever we have our plunger. And so I'm going to ask for another volunteer, my last volunteer. Anybody want to come up? This is the most dangerous one. I'm just kidding. But you will need gloves. Anybody want to come up? All right. And what's your name?
Roxanne.
Roxanne. Hi, Roxanne.
Hello.
I'm going to throw those gloves on because I don't want you to cut yourself there.
Oh, goody. Okay. Safety first.
Yeah. Oh, Grace, can I'm going to try to get this centered better.
Centered?
Yeah.
If I scream, I apologize.
Shoot.
Open.
Oh, yeah.
Open it already.
Yeah, okay.
Okay.
Sorry. Okay. Yeah. Yeah. All right, here's what we're going to do, Roxanne. I'm going to have you basically drive this in and out and describe what you feel. Now, as you push it in one direction, you should feel a resistance. And as it changes in direction and the lever drives this up into the plunger, you should feel a little bit of release in that resistance.
Okay.
And as you pull it back in the other direction, you should feel the resistance again.
Okay.
I'm going to help hold this down because
Okay.
can you push it?
So, lots of
Yeah,
resistance?
yeah.
Oh my gosh, yeah. And then it releases and then it gets hard
And
again.
it gets hard again.
Yep.
Yep. Great. Thank you very much. All right.
need gloves.
Oh, good. Well, wasn't sure. And so this is the system that we built and we tested. And so Grace Soller over here is the student that tested it for her master's thesis, and it came out really well. And really quick, I don't have a lot of time left, but I wanted to show you sort of the process. Do I have a few minutes? A couple minutes? Okay. So first I wanted to let you know that all of my research starts here on sheets of paper scattered all over my desk, which have drawings of things and equations, because I'm trying to figure out the math before I go any further. And so you can actually see here the little rack and lever system. This is probably from like 10 years ago, rack and lever system. And I'm basically trying to figure out the math for the concept. Then after we do that, after we figure out the concept works, then we want to design and we want to test the system. And so what we do is we design the system in a CAD program. So we design all the components in a CAD program. And so this is the design of our lever system, this system here, right? So just two different views, with the plate, without the plate. And then this is a CAD drawing of the overall system. And so the way that we tested this system was not by Grace or me pushing or pulling on it. We have an electric actuator, which basically we use to drive it back and forth in a sinusoidal pattern. So back and forth, back and forth. Because what we're trying to do is verify the concept. And so this is what the system looked like in our lab. Now we did two versions. This version, you can see our plunger there, right? plunger. We did a second version, which actually uses a sensor here. I'm only bringing that up because I have a video, and the video, we only took the video of the one with the sensor. But it works the exact same way. And so our actuator over here is driving the system back and forth. And what we have here is a plot of the force versus the displacement. And I might have been blocking that when you could first initially see it, but there it is. This is a real-time plot of what's happening over here. We're measuring the force, we're measuring the position, and this is the plot. And so you can see the system. Every time there's a change in direction, this goes up, triggers the valve to open and close, and we get this drop in force. And of course, the area underneath this curve is equal to? Energy dissipated by the damper, yeah. That's it. Are there any questions? Any questions? Yes.
So how close are you to actually implementing this on a bridge or something?
Grace, how close are we? Grace is working on this for her PhD. So what we're trying to do now is we're trying to scale this up to a almost full-size system, and then do the similar testing on a full-size damper, which is the next step to trying to get this into practice. Yes?
So when you apply this structure, you have to take into account like the natural frequencies of the structure to get the sizing of it, or resonance, or anything else?
Yeah, the question was, when you install this in a structure, do you have to consider the frequencies of the structure in order to size the damper? And that's one of the things I was mentioning before. The nice thing about this damper is it's based on deformations. So we already have a design deformation for the structure, so we would just size this for that deformation. Yeah. Yes?
Is this something you're designing that could be retrofitted to buildings?
Yes, absolutely.
Okay, not just for me.
Yeah, so sorry. That's a great question. The question was, is this something that could be retrofitted to buildings, or it could only be added into a new construction? It definitely could be retrofitted. The problem with retrofitting is that the system, if you have a structure and it needs to be retrofitted, that structure is probably not designed to carry the forces from the energy dissipation device, which means you would have to reinforce the structure. But yes. Are there any other questions? Yes.
I just have to ask, so are you one of those people where when you go on vacation, you say, stop the car, there's a dampener, I need to take a picture?
I do, yeah. I love seeing those things. Yeah. It's fascinating to me because I do all my work here, and then I finally get to get out and see them. So absolutely, yes.
Thank you very much.
All right. Yeah, thank you. Thank you.